Stanford University.
Hello, everyone. Welcome to the Stanford Seminar on People, Computers, and Design. I'm Scott Clemmer, and I'd like to welcome you today to the first of 3 weeks in a row looking at large online collaboration and crowdsourcing. And next week, our speaker is going to be Judd Anton from Yahoo. The week after that, we have Adrian Truel of CMU. And today, we have Dan Weld. And I'm really glad we were able to get Dan down here. I met Dan in probably 2003 or 4 when giving a talk up at the University of Washington. And the creative energy that I experienced when meeting with Dan has made me feel always like he's somebody that I want to have on our team. And by that I mean the HCI team or whatever team we're involved in. And we're really fortunate that Dan felt the same thing. And so Dan is an artificial intelligence researcher who's done a number of interesting things over the years. He's done a number of interesting research projects. He also founded NetBot, which was acquired by a number of companies, and he's a fellow of the ACM and AAAI. And in the past few years, Dan has turned a lot of his research to looking at applying artificial intelligence techniques to problems of human-computer interaction. He was the supervisor of Christoph Gaius, now on the faculty at Harvard. Christoph was down here a year or two ago talking about his dissertation research on a system called Supple, which automatically generates user interfaces. And it's one of the projects that I probably point people to more than any other. And so I'm tremendously happy that, that Dan has joined our team and agreed to join us today for this seminar.
Thank you. It's a pleasure to be here. I wanted to start out, I guess, as Scott mentioned. Actually, my background is artificial intelligence, and I work on a number of different topics. I guess the thing that tries to integrate them all together is the idea of making computers easier to use. I'm going to be talking about crowdsourcing today, but I'm also interested in how to use AI and machine learning techniques to automatically read news stories and text on the web. And have also done some work on adaptive interfaces. In the context of crowdsourcing, I want to give special thanks to my colleagues and collaborators, Mawsum, Pong Dai, and Chris Lin, as well, who've basically jointly developed a lot of the work I'm going to talk about today, and then a number of other faculty and students who've been quite formative in its development. I also want to start and say I haven't given this talk before and put it together rather quickly, so there may well be rough spots, and I'd like to use that as an encouragement for people to ask questions if I'm not being clear. I wanted to start by just thinking about how, now that we've got the internet connecting large numbers of people together, we can motivate them to do things. And people have proposed many different mechanisms, and I'll just sort of categorize them in terms of economic mechanisms, such as Mechanical Turk and some other systems where people come together and get paid. There's also a sort of a sense of altruism or community working together to build things like Wikipedia and maybe gain social standing in those communities. These have caused quite amazing artifacts to be developed. There's also ways of leveraging the actions that we do just for our own personal benefit. So here, if I go to Netflix, I might choose specific movies that I'm interested in watching, and yet as a side effect of many people making their own choices, Netflix is able to give better recommendations. And finally, a hot topic is how to make things fun, and by having games with a purpose, get people to build things. So some of my colleagues at University of Washington have built a system that gets groups of players together to fold proteins and come up with the three-dimensional conformation of some key AIDS molecules. There's also Picture It, which is kind of a neat game that allows one to build up detailed maps of areas, and many more examples. What I'm going to do today is focus largely on the economic motivation. At the end of the talk, I'm going to come back and talk a little bit about how a sense of community and a set of people working together for a common purpose can be amplified by AI techniques. In some sense, I actually think that's the most interesting direction to go, but I'm only beginning to come up with some ideas about how to tackle that. So within all of these contexts, but certainly especially in the economically motivated crowdsourcing, a key issue is the idea of a workflow, a set of maybe smaller jobs, perhaps done by one person, or a set of different people coming together that allows individual efforts, possibly unreliable or with inaccurate results in the individual component pieces, to get put together to build some sort of larger artifact. If you do have these sort of unreliable workers participating, you need to have checks and balances that will combine them together for reliability. So that's what I mean by a workflow. Ways of managing workers and sort of keeping track of how accurate they are and building these things together. And a key example is Greg Little's Turkit system, which is a way of building these workflows, sort of a programming language for designing these workflows very, very quickly. And there's been a number of other systems more recently that do similar types of platform tasks. And my high-level comment is going to be, although these existing platform layers add a lot of benefit, they still are inadequate, and there's many more things that need to be done. In particular, most of the platforms that have been proposed don't really have any support for automatically learning various parameters you need to control the workflow, or optimizing the workflow itself and having the results that come out of it be more effective. There's also the need to actually build models of the individual workers to find out how accurate they might be at certain kinds of tasks, also extending that to understand what kinds of tasks the workers like. And then finally, in the course of executing a workflow, depending on who's actually been working on it so far, you can optimize the workflow in sort of mid-execution, and I'll be talking about that at length today. It's a hard problem, so putting all of these workers together is challenging, like herding cats. I feel a little bit embarrassed with this cheesy picture here. Even more embarrassed with the cheesy name that we came up with for the system we're building. Clowder, in fact, is the word for a herd of cats or a group of cats. And so that's the name of our system. And what is it? At the highest level, what we're trying to do is take AI and decision theoretic techniques and put them together to control these crowdsourced workflows. So there's a set of components. The first one is the idea of describing these workflows in a declarative language, and we use hierarchical task networks out of automated planning as our representation. I'll give some illustrations of that a little bit later. We're trying to build up models that our AI system can use to manage these workflows. And the idea is to have shared models for different kinds of tasks, and that will sort of serve as the basis for, or the prior for machine learning algorithms that are going to better tune their understanding of how these things work. We also want to have some way of modeling workers, and I'll talk a fair amount, a sequence of increasingly elaborate models of workers. And then we're going to put it all together with decision theoretic control. So here is sort of a high-level picture of the system that we're building. To be honest, it's a little bit vaporware, but we've built parts of it, and we're hoping to have a complete implementation by this summer. At the top, you can see sort of a library of common workflows. That's in the HTN library. There's a decision theoretic planner that puts those together and creates an individual workflow, which then gets rendered into something like HTML that workers can do. So that's the rendered job. At that point, the sort of central AI module is going to be controlling the execution of this system using its understanding of workers and their competencies, and send it out to the marketplace where people will do their individual tasks. And watching all of this is a learning algorithm that tries to improve its performance over time. Scott talked about some work that my student Christoph Gaios has done in automatically optimizing user interfaces. We imagine using those kinds of ideas to try to come up with the best rendition, say HTML rendition of the individual workflows for component jobs. Here's an example of something out of Christoph's thesis. And it's a particular interface that's been rendered in several different ways for people with different visual competencies and physical preferences. His system built all of these interfaces just from a model of what the individual people preferred and some measurements about exactly what their motor uses are. So we imagine doing the same kind of thing with these interfaces that we're sending out towards marketplaces like Mechanical Turk. At the core of the system is this decision theoretic planner, and it uses something called a partially observable Markov decision process as a way of modeling its interaction with the marketplace. I'm not going to go into the details of Markov decision processes and so on, but it's a simple formalism out of operations research that is useful for thinking about probabilistic planning. What I want to do to try to illustrate this is start with probably the simplest thing, and that is trying to guarantee quality results out of a simple job that you send out to the marketplace. And Panos Apiriotis has commented that this is perhaps the single biggest barrier for the adoption of Amazon's Mechanical Turk marketplace is the difficulty in getting individual workers to produce high quality results. In fact, recently it's become even harder with more and more spammers entering the market. And that causes people who are trying to actually get real work done on Mechanical Turk to try to automatically detect when people are spammers rather than legitimate workers trying to do a good job. To automatically reward diligent workers as a way of keeping them incented so that the population of spammers doesn't go to 100%. And to try to figure out some way of combining and aggregating results to achieve high quality results when the individual jobs may be noisy. And the simplest mechanism you can imagine doing is asking multiple people. If you've got workers that aren't necessarily doing their job, you can ask multiple people to do the same job over and over again, and then take a majority vote to see what we believe the correct answer is. This is kind of a very wasteful process, but it happens to be one that's used enormously in practice today. What you can try to do is by watching individual behavior and hoping that if a worker starts out doing good work, then they'll stay doing that. That you can learn a model of their accuracy and perhaps use that in weighting things in the future. And then we'll be talking about more complex workflows for putting these things together in a little bit. So there's an interesting result actually by Ryan Snow here at Stanford that talks about how for some simple natural language jobs you can actually achieve better results than experts simply by voting these casual users, and that was pretty exciting results. But we can do better than majority voting. The first thing we need to realize, though, is that this assumption that people make, and sort of at the basis of voting and all of the other models, is independence of different workers. And is it really true that the performance of different workers is independent? I think it's clear the answer is no. So if I ask you guys which of those two shapes is larger, I'm guessing that you will all agree that that's right. And so probably the accuracy, the result of one person is going to be dependent on the result of another. On the other hand, yeah, which one's bigger?
The one on the right is totally bigger. I don't know why you're asking this. No.
One in every crowd.
I might have a misunderstanding of what independent means. So I take independent to mean that I'm not using information from Jeff's answer to produce my answer.
So I'm using independence to say, thank you for slowing me down. I'm using independence to say that the chance of your making a mistake on this job is independent of the probability that Jeff is going to make a mistake on this job. So if I know that Jeff has gotten it right, that doesn't affect my guess as to whether you're going to get it right.
All right. I'll pedantically argue that workers are independent, but workers' answers are not. I think that's a great point. I shouldn't have said workers are independent, because workers are independent. The correctness of a worker's answer is independent. That's an assumption that many people have made. The argument that I was just starting to make here is that in many cases it's not true. For example, some problems, here it's actually a much harder problem to decide which of these two shapes has a greater size. And so we can say that this problem is easy and this problem is hard. And obviously, on hard problems, people are, even good workers are more likely to make a mistake. On easy problems, they're more likely to get it right. And by taking into account the difficulty of a problem, we can do better. So what we want to adopt in our more accurate model that we're going to use to improve upon majority voting is this notion of conditional independence. So we're going to assume that the accuracy of an individual worker is independent of another worker once we've conditioned on whether or not that problem is hard or easy. This is, yeah.
Is one of the places that you're going with this, that with the circle and the triangle, I don't know, it might be the case that due to human psychology, most people say the circle is bigger when in fact the triangle is bigger.
Yep.
Like the people's answers are correlated in the wrong direction. Is that, I mean, so it could be that majority voting in that case would be wrong. If you took the majority of answers, you'd get the wrong answer because most people think the wrong thing.
I think there's actually a couple things going on in what you were just saying. So certainly the errors are definitely going to be correlated, and we'll see, and I'll talk very briefly about ways of dealing with that later on. But a separate thing is a key assumption that we're going to be making in many of our models, and that is that on average workers are right. If on average workers are wrong, then it's going to be very hard to get to do anything productive with these kinds of answers. Yeah.
I apologize if I'm skipping ahead in your talk, but I'm wondering if you're going to add more nuance to intrinsic difficulty in the sense that there is a problem and then there is a verification of that answer. And in this case, this is a great example because the problem and the verification of one's answer is equally difficult. But that's not true in practice, and that seems like a potentially interesting distinction to make when trying to do quality control for crowdsourced work.
Yeah, that's an
right?
interesting point. No, I'm not actually going to come back and try to tease that out, but I think you're right that is something that one could try to do. In particular, it's going to affect the construction of the workflows. I'm not sure if it's going to affect our mathematical modeling of the workflows. So an example would be, and as an advertisement for Michael Bernstein, who's, I guess, giving a talk here next week, but Scott didn't mention, is one of the crowdsourcing crowd that you guys have. I'll be talking a few minutes later about one of his workflows, the find, fix, verify. And I guess the key idea is it's actually easier to break up a repair action into two component tasks. Continuing with this model, what we are going to do is model the difficulty. It's a very, very simple model, but we've got to start someplace. We're going to model the difficulty of a task as simply a real number between 0 and 1. And the idea is that if it's a difficulty of 0, it's really, really easy. That means everybody is going to get it right. If, on the other hand, it's got a difficulty of 1, that means everybody is going to do no better than random chance. Notice the assumption I'm making here is that the workers are not malevolent. They're not trying to get it wrong. Some of them may be lazy or bad, but they're not actually deliberately trying to mess things up. So what our model is trying to take into account both the effectiveness of a worker and the difficulty of a task. And the idea is that we have somebody, and I'm going to restrict myself to binary tasks that I'll call voting tasks or ballot tasks. A good worker is somebody where this curve sort of bows out in a convex manner, whereas a bad worker is somebody where their results sort of go down more quickly. And this is sort of the basic parametric model that we're going to be using in our first model, which we're learning for the workers as they're acting. Again, it's a very, very simple model. It doesn't take into account that certain kinds of tasks Joe might do well, other kinds of tasks Sue might do well, but it's a start. Any questions, though, before I keep going? So with that, we put together, and somehow I think an earlier slide got skipped, but we put together a graphical model where each of those circles is a random variable. And I apologize for the labels, which were on the graph that somehow got skipped earlier. D is the difficulty of this particular question. The V there is the actual true answer to this particular question. B is the ballot that is returned, so it's the one variable that we actually get to observe. And then the gamma over there is the worker's accuracy. So the actual result that gets returned, the ballot B, is a probabilistic function of all of those other variables. The true answer, how difficult the problem is, and how accurate the worker is. Using this model where we're actually learning the parameters of the workers and then using that to combine them together to predict what the correct answer is, we can see that we can actually do much better than with simple majority voting. In fact, our system can get both higher accuracy, almost 80% accurate, even on with on average workers that aren't particularly accurate. And furthermore, we can reach the same accuracy as the majority vote model with considerably less money. So that kind of probabilistic model of worker accuracies actually turns out to be extremely promising. And I'm going to skip the details about exactly the learning algorithms we use to get that, although I'll highlight some of them later. And people have taken these kinds of models and extended in a number of different directions. I'm going to actually go in a different way and talk about, at the highest level, two ways of learning these parameter values to drive such a model. The most obvious thing you can imagine doing is supervised learning. And the basic idea here is maybe you've got gold standard answers and you mix in some questions where you know the answer and see whether the people are getting it right. That way you know exactly how well the particular worker is doing. And there's a number of systems that do this. So probably with these kinds of supervised learning approaches, we're going to be able to learn our estimates more accurately than with other techniques, although not 100% sure. But there's a bunch of problems. So one is you actually need to have these manually labeled gold standard answers. We're obviously not getting useful work out of the workers when they are answering the questions to which we already know the answers. In fact, there was a talk by some folks at Crowdflower at the Human Computation Workshop this summer, which showed that the spammers were actually spending quite a bit of time learning what all of the gold standard questions were and what their answers were and sharing them amongst themselves. And so it becomes a little bit of an arms race trying to do this more effectively. But I guess the bigger question is, what if the kinds of questions you're asking are subjective decisions where there are no gold truth answers known a priori? How do you use supervised learning in a context like that? The alternative is to use unsupervised learning. And here we've got no label data. We don't know what the gold truth might be. And we need to do some sort of probabilistic inference to estimate the parameters. We need at the same time to estimate how good the workers are and how difficult the questions are and what the right answers are. And you can use an algorithm called expectation maximization to do this. So the probabilistic model we use here is the following one. It's very similar to what I showed you a minute or two ago, but I'm going to be asking a large number of questions. So this box here basically means, this is like a Bayesian belief network. It's called a plate model. The boxes basically mean we've got a template and we're going to make many copies of the variables inside that box. So here I've got a box labeled M. That's the number of questions. And so each of those M questions is going to have its own correct answer and its own difficulty. Similar to this box over here is one for workers. So inside I'm going to have one variable showing the accuracy or the laziness, if you will, of each of the workers. And then this variable B is inside both boxes. So that means I've got one copy for every pair of worker and question. And we're using this model to drive our expectation maximization algorithm. Given a bunch of data, we're going to try to put it all together. And without going into the mathematical details, the intuition here is simply that if you've got one person who disagrees with all of the other people, then they're probably a spammer. On the other hand, if you've got one person who agrees in general with all the other people, that's probably a good worker. And in fact, we have an estimate now of who's a good worker. So other people who agree with the good worker, the people who we believe are good workers, they're probably good workers too. And sort of by iteratively making these estimations, we can come up with our estimate about exactly how good each worker is, what the true answers are, and also how difficult the various questions are. So it's sort of a coordinate gradient ascent as we're optimizing the value of each of these parameters. So far, I've just talked about very simple kind of questions. I've focused on just asking people yes, no questions. And now what I want to do is try to put that all together into more complicated workflows. As I said earlier, by having this notion of workflows, we can actually combine these individual, very small pieces of work into more interesting, higher level tasks. For example, a Seattle startup company called Casting Words does audio transcriptions by breaking the individual MPEG files into smaller audio files, asking people to transcribe the individual pieces and asking other people to judge whether or not it was a good transcription. Handwriting recognition, various other examples of ways that we can construct these workflows. And Michael Bernstein will be talking about a really cool workflow that he uses to get actually a rapid-fired crowd inside a word processor helping you with editing tasks. I'm going to pick a particular example from Greg Little's thesis. The specific overall arching model of the workflow is something called iterative improvement, where we might have an image and we're trying to do handwriting recognition. I don't know how many of you can actually decipher this rather challenging script. Greg can, yeah, what a surprise. So I don't know if Greg actually did it himself, but he built a program which basically asked people to go out there and make an attempt at deciphering it, and then had various people voting as whether or not they believed that that actually was correct, and going around and having another person try to decipher it and figuring out which one's better and which parts of it are better, until finally, after iterating over it a number of times, the sort of crowd as a whole executing this workflow was able to do an almost perfect translation of this indecipherable script. There's still a couple words that they got wrong according to ground truth, but I might have gotten them wrong too. Another example also out of Greg's thesis is, given an image, could you ask people to come up with an English language description of the image? And if you do, you go out there, you might get a description like that. But by doing a more complicated workflow where you ask somebody not just to come up with a description, but now you go to a new worker and you say, here's a picture, here's a description, can you improve the description and make it better? And then after that, you go to yet another person and you say, here's a picture, here's two descriptions, which of the descriptions is the better description? And once you figure out, maybe by having multiple people vote, which is the best description, you now go and try to improve that in turn. And you go around this loop a number of times until you get a better and better description. And Greg showed that after going around, I think it was 8 times, you get a description like this, which is a heck of a lot better description than I could have written. So the high-level point is even a simple workflow like this iterative improvement workflow can really yield some pretty impressive results. And what we tried to do next was to see if we could control the overall execution of these workflows better. So back to the architecture of our Clowder system, what we wanted to do was model these things as a probabilistic decision-making process, a partially observable Markov decision process, where the system at every time is trying to figure out what is the optimal action it should do to optimize some sort of utility function, which is basically trading off the quality of the description with the cost it's paid in workers so far. So we modeled that as a partially observable Markov decision process. This is essentially a search process where each of the states is a belief state. And in our case, basically what the system is doing is it's just trying to say, for this particular description I have at hand, at any point in time it's got maybe 2 descriptions, how good a description is that? And the actions that the system can execute are things like ask another person to vote which of these 2 descriptions is better. Or another action might be pick one of the descriptions and ask somebody to try to improve that. And our system basically builds up and learns a probabilistic model of how much better the description is going to be if we try to improve it with this worker with this particular accuracy. And the overall objective is to maximize the quality of the description minus all the costs you had to pay to the workers. And at a certain point, our system's going to say, you know, I don't think that spending any more money to have extra jobs go on is going to make this much better, so we should just return it to the person who made the request in the first place. So just to give you an idea about how the system works, we start off with our initial description, which I'll call an artifact to make it clear it's more general than just descriptions of pictures. And our system has a probability distribution of how good that description is. And again, we're just modeling the quality of the description as a number between 0 and 1. And I can tell you more about what the meaning is behind that, but it doesn't really matter. So we have a probability distribution that says it's probably not very good, very small chance that the quality of the description is 1 way out on the right-hand side. And so our system can decide, gee, should we try to improve it? If the answer is yes, it generates a job, sends it out to Mechanical Turk, and asks a worker to try to come up with an improved description. That comes back from the crowd, and now we have a probability distribution, again from a learned model, that says how good is this description probably going to be? And we don't really know exactly how it is, so one way we could do is try to figure out whether it's better than the first description. We can do that by executing a voting job. So if the system's not sure enough about the quality of the new artifact, it's going to go off and execute a voting job. Somebody's going to come back and say description A is better. That's going to revise our system's probability distribution. It's going to come back here and again say, well, am I confident enough about how good this description is? If not, it's going to execute another one. If the voter, suppose the voter agrees, now we have a more skewed description. We believe that, that it's a better artifact, and we decide, well, let's see which of these 2 artifacts is the better one. You can basically look at the maximum likelihood estimation of the quality and decide, okay, it looks like this one's the better one, so we're going to throw away the other one, and now we're back in the situation where we started. We could decide this artifact's good enough, I'm going to return it, or maybe our system says, I think probabilistically I should go around this loop some more. So at a visual level, that's how our controller is working. You can do a similar model with Michael Bernstein's find, fix, verify workflow, which I won't go into detail, but for those of you who've seen his system before, for example, the fix and verify is very much like the steps in the iterative improvement. And so we believe we can use a very similar model here, although we haven't actually done experiments to demonstrate that it works in practice. instead, sticking with iterative improvement, we did go off to Mechanical Turk, and using our system, here I've called it Turk control. That was the first implementation that's leading its way towards our eventual system clouder. You can see that I've plotted here the quality of the resulting artifact, the resulting description produced by our system versus the quality produced by a hand-coded policy, which basically asks two people which description is better. If they agree, it says, OK, that's it. Otherwise, it asks a third and takes the majority vote. So anything right on that x equals y axis means that both systems did things equally accurately. And you can see most of the points are below the line, which means our system did better. Those results may not look super impressive, but I should point out that this is a logarithmic scale. So actually, the fact that we've got a fair amount of the points in the lower right really is a very good thing. So another way you can look at it is, supposing you're spending the same amount of money, how much better is the quality in our system? It's actually quite a bit better, statistically significantly better. Another question you can ask is, suppose we want to actually use the two different policies to generate descriptions of the same quality. How much more does it cost? Turns out it costs about 30% more money to do it with the hand-coded policy I described rather than our system. More interesting, perhaps, is looking at the behavior of the system. So interestingly, our system, on a number of the images that we tried to get descriptions, actually asked fewer people to do things, and yet somehow it knew what it was doing, because in most of those cases, it actually came up with better descriptions, even though it had less people working on them. In one case, it only had one vote of a very challenging problem, but it happened to have believed that that worker was a great worker, and so it just decided to go ahead with it. So in general, it seemed to be doing intelligent ballot use. One thing it did actually sort of seemed like a mistake to us until we thought about it more. So looking at how ballot is used by this hand-coded policy, you can see on average, as you make successive improvements to your description, how many voters do we ask? There's sort of a trade-off, right? You can either spend your money to try to ask more people to vote between the two descriptions to see which one's better, or you could have less people voting. That saves you some money. Now you could use that money to have more people actually trying to improve the description. So the question is, how do you do that trade-off? And the hand-coded policy basically always says it uses about 2.5 votes at every cycle, right? Because what it does is ask two people. If they agree, which they do half the time, it stops. Otherwise, it asks a third person. It's sort of a reasonable strategy. What Turk control does is the following behavior. At the beginning, we thought this was a bug. It's not asking anybody, right? And then it actually starts asking lots of people, a lot more than 2, 3, and so on. And eventually we realized at the beginning it's actually pretty easy to improve the description. And so our system just assumed that the person was actually coming up with a better description. But then after a while, it actually gets much, much harder to improve the description. And so Turk control started basically using all of its money to try to make these harder decisions. And it figured this out all on its own as a result of this POMDP model, which we thought was pretty cool. So popping up to yet another level, I want to think about multiple different workflows and how we might switch between these different workflows. I'm going to give you a high-level example first and then show in practice how to do it in one concrete case. So the basic idea is, suppose we want to do a translation task where we've got a description of one language, English, and we want to translate it into Polish. Well, one approach would be to have two humans do a translation and then have a set of voters figure out which is the best translation. That's one workflow you imagine using. Another thing you might do is you might have a machine, an automated translator, translate between the languages. But that's probably going to introduce a bunch of errors. And so then you might have people do a sort of a proofreading step afterwards to try to make it better. In fact, how we do the proofread, another thing you could do is you don't have anybody who speaks both English and Polish. So first you translate it into French, and then you have somebody translate it from French to Polish. So that's another possible workflow. Not clear it's a particularly good one. And then furthermore, the idea is these things are hierarchical. So as you've got a library of workflows, you can expand them out. So we might want to use a find, fix, verify workflow to implement this sort of proofreading step. That's the high level idea. And what the planning algorithm now needs to do is decide which of these workflows is the best one to do. Let me just say for a minute what I believe goes on in practice today. And that is a human expert goes out and they consider a couple different ways of getting the job done. And they sort of follow an iterative design process where they come up with an interface for executing one of these workflows. They send it out. They get a bunch of people to work on it. Maybe they ask comments. They figure out where the confusions are. They make it a little bit better. They come up with a couple different alternatives. And then they run those out there, and they see what's the overall accuracy. How well are these doing? And then they find the one that seems to be the best, and they say, okay, this is it. Now I'm going to run my next 200 million jobs using that workflow. And that's a pretty reasonable strategy. But what's interesting is it's not the best strategy. So interestingly, it's actually useful to keep those suboptimal workflows around. And in particular, in a number of cases, you can get synergy by switching between different workflows and having different people do different things. So it might actually be useful in certain cases to try a workflow which on average is not so good. So here's an example to make it concrete. In my other life, I do machine reading, and one component task there is looking at noun phrases and text and trying to understand what kind of an object is that. So in particular, we see in that text at the very top, we see the word Washington in boldface. And we want to know, is that the city, or is that the state, or is that the mountain, or is that, I don't know what else, there's lots of University of Washington. There's many possible types that this Washington could be. Suppose we just limit ourselves to the capital and the state. It's very useful from a machine reading point of view if we know what kind of a thing this is. So there's a couple different ways you can imagine getting workers on Mechanical Turk to answer this question. One thing you can imagine doing is asking them something like we say over here. Is it a location, or is it a city? Basically, pick out the tags. This is kind of a bad example. It should be location, state, and this one says city. But you get the idea. Somebody could choose which tag it is. Or a different workflow we could ask them to do is say, which of these things seems to be the corresponding Wikipedia entry? So these are two different workflows. We actually experimented with both. Do people have intuitions of which one of these is going to be easier and more accurate for people to do? Yeah. You think it's this one? On average, it's this one. This is a bad example with bad tags. But the interesting thing is, actually, it's useful to keep them both around. And the intuition here is that this idea of difficulty is oftentimes problem dependent. So some problems, most problems might be easier in this workflow, but some problems might, like this one, might be confusing in this workflow, and yet over here, if you ask them the same question this way, they'd be very, very easy. And so the idea is our system, as it's going along, is going to be estimating how hard a problem is it that I'm asking? How hard a problem is it with this particular workflow? And might it be easier if I switch to a different workflow and get better results? This is the overall model where our system basically goes out and it tries to switch between these different ways of doing the task. To drive this, we need to have a better learning algorithm. And I hope I don't make your eyes glaze over with this more complicated plate model. It's basically the same model we saw before, but it has an extra plate around it, which is one for each possible way of accomplishing the task, one for each workflow. And this is work that is done by our student Chris Lin, and he built an unsupervised learning algorithm that learns these models using expectation maximization. And he put that inside a reinforcement learning system, which goes out and starts asking people to do jobs. And as they're doing the jobs, it learns up better and better models of these parameters so that it can figure out when to switch between the workflows in the future. I'm going to skip the details of the POMDP and the details of the learning and go straight to the experiments. The bottom line is that especially in cases where you really want to get the right result, where having correctness matters, this kind of ability to switch between the different workflows matters enormously, and the system does much better. So I'm about to switch to the more speculative part of the talk, so I just want to point out that the high-level message I hope to get across is that whether you're talking about simple workflows or complicated workflows, you want to have AI support to do these kinds of decisions. I haven't talked about automating the pricing decision, but certainly the parameter estimation and control in comparison between different workflows is something I believe that we want to do every time. And so we're trying to put this together into the system which uses hierarchical network task blending to make this all a seamless process that you can run in a reinforcement learning context. You just give it your models, and it goes out there, and it figures out what's the most cost-effective thing to do. At the beginning of the talk, I said that most of our attention's been on this sort of economic motivation, but there's other ways of motivating people. And I wanted to come back to these more sort of social, collaborative things at the end of my talk. And I'm getting increasingly nervous as I go because this work is very half-baked, but I'm hoping to get useful feedback. I'll start with something that's a little bit more baked. So what we like to do is we like to have a community of people that are coming together and building some artifact. Maybe they're editing web pages, maybe they're doing something like that, and they're working together. And we like to figure out some way we can use AI to make that work better. And the problem is, where the heck do you get this community from? Well, the natural inspiration for me was to somehow tie this in with our machine reading project. So here, we've done some kind of interesting, we've built a whole bunch of systems. They're listed up at the top, but all of them sort of work in the same way of trying to understand natural language text and pull out relational values. So for example, they might be able to go from text like this that you would find in a Wikipedia page and actually fill in entries on an info box summary of the page automatically by themselves. And they work pretty well. But because they're using unsupervised learning, they don't work perfectly, and we'd like to get them better and better. The hope is by having people correct them, we could actually improve the training data and learn how to do them better. So, so how do we get the crowd? Well, the idea would be if we can somehow get the crowd, maybe by creating these resources from scratch, then if we could tie these two systems together, we could actually create a feedback cycle. So I'll draw it that way. The idea is every time a person goes in and makes edits, we're actually improving the training data, which is going to cause our information extraction system to learn a better model, which is going to allow it to better extract more data, which is going to make our resource better, and that's going to increase the number of people who come to it, and that's going to increase the number of edits, and we'll be able to make the system better and better. This is the motivation of a system that we're trying to build, but what I'm actually showing you now is one that we built a few years ago. I'm going to give you just a couple more phrases about that before I go into what I'm trying to build. We actually wanted to evaluate this in the context of Wikipedia, and we didn't want to abuse our readers. And so what we tried to do is come up with 3 different interfaces that would incentivize them to make these edits and to actually improve the training data. Sort of really natural interfaces. Here's an example of one. So This is our augmented content for Wikipedia. And if a person sort of hovers over one of those highlight yellow things, then our system comes up and asks a question. Can you confirm the extraction here? Or if a person, right, so there's the extraction. If a person hovers over here, then it pops up something and saying, well, gosh, we think that the value of that info box is August 22nd because it says it in the sentence. Do you think that's right or not? So what we really wanted to do is we wanted to put this stuff up on Wikipedia. So I sent an email off. Wikipedia has a robots exclusion policy. You have to get permission before you have any automated content or any automated robot that's modifying things. So I sent an email off to the powers that be and asked permission. I explained that our information extraction algorithms had accuracy as high as 98%, and we'd gotten a best paper prize for the work at such and such a conference, and I was the mumbly mumble professor of computer science at something, and would it be okay if we had our robot running over their info boxes? And I wasn't sure what I was going to get back from the bureaucracy, but I didn't expect what I got, which was an extremely fast answer saying, no, absolutely not. And it turns out it was written by a 14-year-old Danish boy. So it was quite a blow to my ego. But he said, he didn't really register this best paper prize and all that other stuff. He just said, I have 20,000 Wikipedia edits under my belt. As far as I can tell, you have none. Okay, so that was out. So that raised the question: how can we actually make this work? Well, we resorted back to money. So what we did is we put a bunch of ads. So we focused on authors. If somebody did a search for Ray Bradbury, we actually placed a Google AdWords advertisement saying, gosh, are you interested in enhanced Wikipedia content? And if so, we would take them to our intelligentwikipedia.org website. And there was a little disclaimer if they wanted to know that this isn't the real Wikipedia and so on. And we now rotated between the different interfaces as well as just a plain old vanilla interface. And there's a lot to say about that experiment. The sort of summaries are that there's sort of different spectrums of these interfaces in terms of how much contribution they got versus how annoying they were. Notice that even the baseline interface was deemed to be quite annoying by people, which I think means that in the course of asking the survey at the end about how annoying they are, they got annoyed. So it's sort of a little bit of Heisenberg uncertainty effect. But with the baseline interface, we got absolutely no contributions at all. And yet with these other interfaces, we actually got people to contribute quite a bit.
Wait a minute, your scale here goes from 2 to 4.
Of intrusiveness? Yeah, well, there was no answers over. No one thought that the interfaces were unobtrusive.
So this exaggerates the differences between the conditions then, by virtue of clipping the endpoints on the
that is true. From an intrusiveness point of view, there's really very little difference. The scale, I believe, was 1 to 5.
Because I would have told the opposite story from this graph that you did, which is on the entire scale, the difference between ours and baseline is minimal. Because you don't know what
sounds a lot better, doesn't it? Okay, I'll tell your story. Yeah, that's much better. So as you can see, we got much higher participation rates with almost negligible increase in the intrusiveness. Thanks, good. So what's the bad news? The bad news is that we actually had to spend $1,500 on all of these AdWords. And if you divide by the number of contributions you got, it turns out each one of those edits where somebody just said, yes, you got it right, no, you didn't, each one of those cost us $10. So it makes you want to go out to Mechanical Turk to ask people to validate that way. So we thought this was a reasonable price to pay for getting a Chi paper, but it certainly isn't a good way to do a long-term scalable study. So if we come back and start thinking about how we're going to do our future research in this area, we need to have some sort of organic traffic. Now I'm entering the truly flaky part of the talk. I'm sorry, it's like I gather you guys don't talk about anything other than online education, so why am I talking about online education to you? It seems like a really hot topic, though. Why not try to do something with online education? And in fact, in this model, you can think about the students as being the crowd. And so we can actually maybe use one of our models to try to determine how well they're doing at the particular topic that they're studying. And in fact, we can also look at the individual problem sets they're working on and try to figure out, which ones are the hard problems and which ones are the easy problems. And then in the context of this, maybe the workflow, the switching between different workflows is different ways of teaching the same material or different micro lectures or so on. And maybe our system could figure out when to try switching between these things given different people and different problems. That's the high-level dream. We haven't built any of this, but that's the dream. We still need to come up with some way of getting traffic. And so the idea here is we could go off and teach these big classes to 160,000 people, but you guys are already doing that. So we thought we'd take a different approach, and that was try to put together an online resource of educational materials. And again, we'd be using AI techniques like page classification, trying to understand when you've got a syllabus page, when you've got a problem set page, when you've got lecture notes, figuring out exactly which topics each of these things is talking about, and extract the content from resources that are out on the web today, and put them together into a better organized system that is easier for people to use to find the things they want, and that would hopefully drive traffic. So we'd be able to bootstrap the traffic and then hopefully get people to make it better. Here is just a really, really rough done in the day before I left to come down here, sort of prototype UI of what this might look like. So you might be able to look at a number of different topics that you're interested in learning about. If you hover over one of those topics, you get some more information about it that's extracted from resources such as Wikipedia. If you click on the summary, you get a number of different possibilities. We're calling out and asking you to try to figure out whether we've extracted things correctly, whether it's useful to you or not. We would have indexes into videos. In fact, what I would hope we would do is index right into the video section where you're describing the particular concept instead of giving somebody the hour-long video, which is the preponderance of what's out there today. Also be able to see lecture slides, also tutorials, hopefully connect people with other people as well. I think one of the most interesting things is trying to automatically extract problems from problem sets that are out there on the web, and we can not only get people to see if we've categorized them correctly, see whether or not they're useful to them, but also try to automate them as we get the answers involved so that we can test things automatically going forward. The summary then is maybe we can use these ideas we've developed in the context of Mechanical Turk to amplify online education. And it's a vision I'm really excited about. I'm hoping to hear feedback from people, but it's very, very early, so we certainly don't have it all figured out. In any case, thank you very much. I appreciate all of your attention. It looks like we have 2 minutes for questions.
We have the room till 2:05, so if you have a few extras, we can
get. Have you thought about how the problem would change if you were designing this from the perspective of the worker rather than the employer? So there's some synergy, but they're not identical interests.
We've thought about that a little bit, and I think that's a direction that deserves a lot more attention. I think the key thing there is to focus not so much on how accurate a worker is, although I think that's important to the worker as well, but more on what kind of a problem it is. Is it the kind of problem that the worker enjoys working on? And obviously, both people benefit if you can identify that, and so I think that's an exciting direction to go. Any other questions? Great, well, thank you very much.
For more, please visit us at stanford.edu.